Hi, everyone. My name is Vincent Conitzer. I spent the last 16 years on the faculty at Duke University. Those were wonderful years, but I'm very happy to be back at CMU. I say back at CMU because I did my PhD in the computer science department in 2006. And so now I'm joining the computer science department again, now as faculty. I also have appointments in the machine learning department, the Department of Philosophy, and the Tepper School of Business. My work is on artificial intelligence broadly, but in particular, multi-agent systems, game theory. Game theory is about settings where you have an agent that is strategic and is acting in an environment with other strategic agents that maybe have different objectives. And so how should they act rationally? That's what game theory is about. I also work in social choice and mechanism design, which are related. And I also work in AI ethics. And all those research directions are now coming together in a new lab that I'm starting here at CMU called the Foundations of Cooperative AI Lab, or FOCAL. So what is FOCAL about? In FOCAL, we're going to rethink the idea of an agent in artificial intelligence, in particular, in the ways in which that affects game theory. So in the ways in which that affects what it means to be a strategic agent. And we'll also be particularly interested in how we can use that to get AI systems to be cooperative, perhaps in ways that humans cannot be cooperative. Here on the right of the slide, I asked you to imagine a situation with two self-driving cars, the orange one and the green one. And they are actually able to send messages to each other while they're driving on the road. And so there's a little story playing out there. I'll let you read it for yourself. The story in some ways is supposed to be a little bit funny. I don't know if it's very funny, but to the extent that it is funny, it's funny because at some level we realize that we don't really expect self-driving cars to behave this way. Right? It's a very anthropomorphic way of thinking about a self-driving car. And yet, I would argue, in AI, we're usually taught to think about agents, the design of AI systems that can act as agents in the world, in this very way. So just as an example of that, let me show you this slide, which is taken from Russell and Norvig, arguably the main AI textbook. And it describes this idea of an agent. So here on the left, we see this idea of an agent, which is this very modular, well-delimited entity in the world that perceives the environment with sensors, has a model of what the world is like, and also a model of how the world changes, and in particular, how it changes in response to its own actions. And it also has a utility function, let's say an objective, preferences over the state of the world. And that is what will guide how it takes actions in the world. Based on that, it can conclude what actions to take. Then it has some kind of effectors with which to influence the environment. And so that's the model of an agent. There's also in particular this question here of a utility function, right? This idea that the agent has some kind of measure of how happy it is with states in the world. And there's always this question of where does that utility function even come from? And traditionally in the AI community, we haven't really worried about that too much. Usually we've taken the perspective that, look, we're just going to make the algorithm as general as possible so that it could work with whatever objective function. And somebody down the line will figure out what the objective function is supposed to be. That has been the traditional model in AI. And maybe that made sense while AI was mostly a research endeavor, mostly in the lab. But now that we see AI deployed broadly in practice, we realize it's not so simple. And we can't just rely on somebody filling in the objective function. We really need to think about tools for figuring out what we really want the AI system to do. So that is one direction. But in our lab, we're also particularly going to look at the left side of this picture over here, this idea that an AI agent would be this modular, well-delimited entity, which I think already doesn't hold up with current practice in AI. For example, you could think about a personal assistant like we have on our phones, right? In some sense, this has long been a dream of the AI community to have personal assistants that work well, that work on our behalf. And in some sense, we have that now, but in some ways, I think it's not quite the way that we anticipated it to be, right? Rather than me having my own personal assistant that is just mine on my phone, instead we have things like Siri. Is Siri on my phone one agent? That doesn't really seem like the correct description of Siri. Is all of Siri across everybody's phones and everywhere, is that just one agent? That also doesn't seem quite right. And so that shows in some sense how this idea of a well-delimited agent already comes under pressure. I want to very quickly show you something a little bit technical that illustrates the kinds of things that we will do in the lab. Here we have the prisoner's dilemma. This is one of the standard examples from game theory. We have two agents, a red one and a blue one, that each have to choose whether to cooperate with the other or to defect on the other, to try to take advantage of the other. They both make a choice. The red agent chooses a row, the blue agent chooses a column. Once they've both chosen, that defines some entry in the matrix, right? If the red one chooses defect and the blue one chooses cooperate, we end up over here. The first number is the utility of the red agent. The second number is the utility of the blue agent, right? So over here, the red agent does very well, taking advantage of the blue agent who tries to cooperate and therefore suffers. The traditional analysis of the prisoner's dilemma says, look, whatever the blue agent does, the red agent is better off defecting, right? If the blue agent cooperates, well, 2 is smaller than 3, so the red agent is better off defecting. But also, if the blue agent defects, then still the red agent is better off defecting and getting 1 instead of 0. And so what we would expect to happen if the agents are selfish is that they both defect. We end up here in the bottom right corner. They each get 1, which is really unfortunate because they could have both got 2, right? If they had only cooperated with each other, that would have been a much better outcome. There's a variety of ways in game theory that you can yet try to get to this cooperation outcome. Here, I'll suggest one that is particularly relevant to AI systems. In particular, imagine that you have an identical twin, right? Maybe some of you watching this video, in fact, have an identical twin, but imagine it's a very extreme case of an identical twin where your whole lives you have always made that same decision every single time that you interacted with each other. And now you play prisoner's dilemma against your twin. You're still selfish, let's assume that. But now there's this argument that says, well, maybe I should cooperate, because if I cooperate, chances are my twin cooperates as well. We always take the same decision. Whereas if I defect, chances are my twin will defect as well, and I will get 1 instead of 2. The reason that we're interested in this here is not because we care about human identical twins for this purpose, but we care about AI systems, which come down to code. And in the end, they may be running the same program for making decisions, right? And so that would be a very extreme case of this, where the two agents are actually using the exact same program in order to decide what to do. And at that point, maybe it makes more sense to cooperate. So that's just a very quick introduction. There are many different ways in which you might get to cooperation. Some of them work for human beings as well, but others, interestingly, I think, work better for AI systems. So I hope that was of interest to you. If it was, this semester, just starting now in the fall of 2022, we're teaching a course on the foundations of cooperative AI, and I hope to see many of you there. Thank you very much.